Now we'll discuss the liquid junction potential. It is very simple concept. So simply a potential which is developed due to contact between two solutions of same or different electrolytes okay, at the junction is called the liquid junction potential. Okay, so it is also called as diffusion potential. Okay, again it is also called as simply the junction potential. Okay, it is represented by capital E and small j. So wherever you will find this symbol, it is termed as liquid junction potential. Okay, so once again I will repeat, liquid junction potential, it is the potential which is developed due to contact between two solutions of same or different electrolytes. Suppose this is electrolyte 1, okay, and this is phase boundary, and this is electrolyte 2. So whatever the potential developed due to activity or concentration difference between these two at the boundary, this is called as the liquid junction potential. Okay, so this is very simple concept. We'll see its origin. So the liquid junction potential arises from diffusion of ions. Okay, so we are talking about the origin, how it originates or how it develops. So the liquid junction potential, it arises from diffusion of ions in the solution across the boundary due to concentration difference of two electrolytes. Okay, so generally the ions diffuse from higher concentrated side to lower concentrated side. Okay, so generally the ion diffuses like this, from higher concentrated side to lower concentrated side. Okay, here whatever will be the faster moving ion, okay, this will move ahead or fast across the boundary, okay, than the slower moving ion, okay, that is from higher concentrated side to lower concentrated side. Okay, so there is separation of charges. Means what? The faster moving ion is moving ahead of slower moving ion. So here the slower moving ions gets accumulated, and here the faster moving ions gets accumulated. So here whatever will be the charge, if the slower moving ion is negative ion, so this side will carry the negative ion, and if the faster moving ion it is positively charged, then this side will acquire the positive charge. Okay, so due to diffusion of ions, the liquid junction potential arises. Okay, due to concentration difference or activity difference. Okay, and generally we have seen the ions diffuse from higher concentrated solution to lower concentrated region. Okay, so we'll take one example. So here liquid junction potential, this is one example. Okay, so in the diagram we have taken 1 molar HCl and 0.01 molar HCl. So this is higher concentrated solution and this is lower concentrated solution. Okay, so this diagram represents the diffusion of ions like this. So here the liquid junction potential between 1 molar HCl and 0.01 molar HCl is shown. So here the H plus ions which are positively charged and Cl minus ions which are negatively charged diffuse across the boundary. So this is porous partition, this is the boundary, phase boundary. So across the boundary from 1 molar to 0.01 molar, that is previously we have seen the ion diffuses from higher concentrated side to lower concentrated side. So ion diffuses from 1 molar HCl to 0.01 molar HCl. Okay, now the H plus ions which are smaller in size, they move fast, okay, than the bulkier Cl minus ions. Okay, so here if you see the size of H plus ion, it is very small as compared to this size of Cl minus ion. So obviously the H plus ions will move faster than this Cl minus ions. Okay, so H plus ions by moving ahead of Cl minus, they goes into this 0.01 molar HCl region, while the Cl minus ions which are bigger in size than the H plus ions, they move slowly and then they remains on this side. So H plus ions move across the boundary to this region, and this side the concentration of H plus ions will get increased on this side. Okay, and here the concentration of negatively charged Cl minus ions is increased on this side. So this side, this portion acquires the negatively charged and this side acquires the positively charged. Okay, so here the separation of charges takes place. Okay, so the concentrated side, this is the concentrated side, this acquires the negative charge due to excess of slow moving Cl minus ions, and the less concentrated side, this acquires the positive charge having faster moving H plus ions. Okay, so in general here I will write the more dilute solution acquires charge of faster moving ion. Okay, while the concentrated side, always acquires the charge of slower moving ion. Okay, so this is very simple. This sets the potential difference at the junction. So here, due to charge separation, of potential is set, and this settle down to a value such that both the ions diffuse at the same rate. So this potential gets settled when the rate of diffusion is same across the boundary, and this is the steady state condition. If the rate of diffusion is same, it is called as the steady state condition. Okay, which is attained rapidly. The potential difference at steady state condition is junction, which contributes to measure this is the junction potential, which contributes to measure the cell EMF. The magnitude of liquid junction potential depends on relative speeds of ion. Okay, so this is magnitude of this, or this liquid junction potential depends on the relative speeds of ions. So this is important part. It can be asked for the MCQ in a coming exam. So the magnitude of liquid junction potential depends on the relative speeds of ion. Okay, so in this by using this diagram, it is very easier to understand how liquid junction potential arises due to diffusion of ions from concentrated site to dilute site. Okay, so I hope all of you have understood this, will understood this concept. It's very easy. Now let me clear this. Okay, so now we'll see the elimination. Okay, we know we have seen the how liquid junction potential arises or originates. Okay, now we'll see how it can be eliminated. Okay, so elimination, here I will write elimination of liquid junction potential. Okay, a lot of efforts have taken to eliminate liquid junction potential, or rather to reduce it to a minimum value. This is often achieved by using salt bridge. So this is one method. You have to use the salt bridge to remove or eliminate the liquid junction potential or to reduce its value. Okay, so salt bridge, we'll discuss some part of salt bridge here. Salt bridge, it is U-shaped tube, okay, which is filled with saturated solution of electrolyte. Okay, so generally the KCl or NH4 NO3, it is used as electrolytes in an agar gel. Okay, so this is the salt bridge is U-shaped tube which contains the saturated solution of electrolytes like KCl and NH4 NO3 in agar gel. So applications of salt bridge is based on two properties. Which are these two properties? Present the two properties used in this. The first property is the ions of bridge electrolyte present in excess over the ions in the electrode compartment. So suppose this is compartment 1, here it is electrode, and electrolytic solution is suppose zinc sulfate, and we are using here the salt bridge like this. So whatever the ions present in the salt bridge, it is excess over the ions present in electrode compartment. So this is one property, so that they carry almost all the current across the boundary. So this is the first property. The second property is the ionic mobilities of both cation and anion nearly equal. Okay, so that is their transport number, that is T plus and T minus. These are the transport numbers of positive and negative ions respectively. So these must be or almost equal. For example, in case of KCl, the TK plus, that is transport number of K plus ion is equal to 0.49, and transport number of Cl minus is equal to 0.51. So these are nearly equal. So the salt bridge which is made up of saturated KCl, it is versatile salt bridge. Okay, so these ions diffuse out of the salt bridge into dilute solution at nearly equal rates. In above conditions, the liquid junction potential is very small, or it is considered to be neglected. So KCl often used in salt bridge. When KCl is cannot be used, for example, in cell contains AgNO3. So if the cell contains AgNO3 electrode or electrolyte, in that we cannot use KCl because AgNO3 reacts with KCl to form the silver halide. So here we cannot use KCl salt bridge. Here we can use the KNO3 salt bridge, KNO3 or NH4NO3. Okay, so the salt bridge will contains these electrolytes that can be used in case of silver nitrate electrode. Okay, so here we have seen the elimination of liquid junction potential. Okay, now we'll see the determination. I hope everybody will understood this. Now we'll see the determination. Here I'll write determination of liquid junction potential. Liquid junction potential can be determined as follows. We have different methods. The first method is A. So here EMF of cell with transference is given by, we have seen in previous lectures, EMF of cell with transference, it is written like this, is equal to EMF of cell plus a liquid junction potential. So this is equation 1. Okay, so this is the EMF of electrode with transference, this is the EMF of cell without transference, and EJ is the liquid junction potential. So simply the liquid junction potential, that is EJ, is equal to EMF of cell with transference minus EMF of cell. Okay, so first of all we have to determine this EMF of cell with transference, and we have to determine the EMF of cell without transference, and if we take the subtraction we'll get easily the liquid junction potential. Okay, so we'll see one example. So here let's take the EMF electrolyte concentration cell with transference, reversible to cation, that is H plus. We have seen its derivation. So the cell can be represented like this: platinum, here H2 gas pressure, and here HCl A1, here HCl A2, here again the H2 gas pressure, and here the platinum. So this is the electrolyte concentration cell with transference, reversible to cation. Okay, so the EMF of this cell can be given like this. We have seen the derivation in previous lectures. So EMF of cell with transference is equal to 2T minus 2.303 RT divided by F, because number of electrons involved is 1, log to the base 10 in case of M2 gamma 2, M1 gamma 1, molality and activity coefficient. Okay, so this is 3 number equation, and EMF of the same cell without transference is given by EMF of cell is equal to 2.303 RT divided by F, log to the base 10. Okay, M2 gamma 2 divided by M1 gamma 1. This is equation number 4. So from equation number 2 we can write like this. So what was the equation? EMF of liquid junction potential is equal to EMF of cell with transference minus EMF of cell without transference. So keeping these two equations in this equation, we can write EMF junction potential is equal to 2t minus 2.303 RT divided by F log to the base 10 M2 gamma 2 divided by M1 gamma 1 minus 2.303, that is equation number 4, RT divided by F log to the base 10 M2 gamma 2 divided by M1 gamma 1. Okay, so this part can be taken out as common part. Let me clear this, keep in mind. Okay, so further step is EMF liquid ignition potential is equal to 2t minus 1, and whatever the common, it is 2.303 RT divided by F log to the base 10 M2 gamma 2 divided by M1 gamma 1. Okay, so this is fifth equation. Now we know t plus t minus is equal to 1. Okay, then 2t minus 1, it can be written like this, t minus t plus. So okay, so this can be written like this from this. So therefore EMF liquid ignition potential is equal to t minus t plus into bracket into 2.303 RT divided by F log to the base 10 M2 gamma 2 divided by M1 gamma 1. So this is equation number 6. So by using this equation, so you can easily calculate the liquid junction potential. So you need to know transport numbers of positive and negative ions and the activities M2 gamma 2 and M1 gamma 1. You can easily determine the liquid junction potentials. Okay, so this is the determination of liquid junction potential, first method. The next method is B method. Now consider the cell with transparency of the type like this: Ag solid, AgCl solid, MCl, that is metal chloride, metal halide having molality, M dash Cl, that means metal only changed, anion remains same molality. Here AgCl solid, silver solid, so this is silver chloride electrode. Okay, so this is the electrolytes are chlorides, both the chlorides of two different univalent cations. Okay, so this is M, this is M dash, that is two different univalent, that is valency 1 univalent cations. Okay, so what can be taken? The HCl KCl, this pair can be taken, or HCl LiCl, this can be taken, or LiCl NaCl, this can be taken. So now when these electrolytes are at same concentration, then EMF of the cell is equal to junction potential. That is EMF of cell with transparency is equal to, since the electrolytes are at same concentration, then we get directly the liquid junction potential. For example, suppose the same electrode can be written like this: Ag solid, AgCl solid. Okay, here we'll take LiCl, which is having activity M is equal to 0.01 molality, and here we have taken NaCl having molality 0.01 again the AgCl solid, Ag solid. Okay, so here the concentration is same, molality is 0.01, here also 0.01. so the total EMF is given by EMF of cell with transference is equal to EMF of cell plus liquid junction potential. So this is equal to 2.303 RT divided by F log to the base 10 A1 upon A2. This equation also we have seen, plus liquid junction potential. Okay, so this is equation number 8. So keep these terms in mind. We'll move further. Let me clear this. So the next part is since this A1 is equal to A2, that is 0.01 mole, molality is equal to, then we'll get the EMF of cell with transference is equal to liquid junction potential, like this. Okay, so this is method B. Now we'll see the method C. Liquid junction potential may also measured by means of two suitable cells as follows. So one first cell, that is potassium amalgam KHG, KCl in bracket M1, that is molality 1, KCl having molality M2, and here the KHG. So here potassium amalgam electrode and here KCl electrolyte having molality M1, KCl electrolyte having molality M2. Okay, so here electrodes are reversible to cation. Okay, because we have used this potassium amalgam electrode. So the total EMF can be given like this. So this is, we can write the E1 is equal to 2.303 RT divided by F log to the base 10 A2 divided by A1 plus Ag. We have seen this equation. Okay, and suppose this is reversible to cation, that is K plus ion. Hence this equation is written like this. If the same cell is made reversible to anion, then we can write the Ag solid, AgCl solid, okay, KCl M1, KCl M2, AgCl solid and Ag. So this is reversible to anion, that is Cl minus ion. Okay, so the E2 is given by, that is EMF of this cell is given by 2.303 RT divided by F, okay, log to the base 10 A1 divided by A2 plus Eg. Okay, so now putting the gamma K plus is equal to gamma Cl minus this activities, will get the liquid junction potential is equal to E1 plus E2 divided by 2. So this is the third method by using which we can easily determine the liquid junction potentials. So here we have seen, let me clear this. I hope you will understand this after watching the video. So let me clear this. Now we have seen the liquid junction potential, then its origin, okay, then its elimination by using Salz bridge, and finally we have seen the determination Okay, in that we have seen the three metals. Okay, so this is very simple point, liquid junction potential. Watch this video clearly and get understood every aspect about the liquid junction potential. Thank you.